Okay, so we're looking at a situation where we have a cylinder of gas. We're assuming it's massless, whatever, and it's surrounded by insulating walls and has a movable piston on top, which is supporting a mass. All right, so this is in equilibrium. I'm going to call this side, just call it number 1. All right, we have an M1, a T1, and a Z1. This is Z1 is the height of the piston here, and so we're going to, by 2 different routes, we're going to go to a situation number 2, where we have T2, M2, Z2, right? So what we've done is we've replaced this mass by this mass, and just for the sake of the problem, we're going to assume this mass is lighter than the first mass, so this piston is just going to gradually move up, and we'll be looking at 2 different ways of doing this, all right? So in the end, what we want to shoot for our two goals are the ratio of the temperatures, so the final temperature over the initial temperature, and also the ratio of the heights. So these are our 2 different goals. All right, so the first way we're going to look at this is what if we suddenly replace M1 with M2. So this is not a quasi-static process, and so I guess, you know, by definition it's not an adiabatic process either, and so it's not. But yeah, on the other hand, it's not extremely quick. So you may have heard about the adiabatic approximation for something like an Otto cycle and an engine, or like an internal combustion engine. Well, we're not going to be able to use that either. And apparently there's some sort of, you don't want to mess up the eigenfunctions of the gas. So you can either go very, very, very slowly. I guess the adiabatic approximation, and maybe it's more like a sudden approximation. I don't know. But so basically, we can't use anything adiabatic. So we're going to use conservation of energy for the first part. So I'll just, so we don't get confused with situation 1 and 2, we are going to just call this first one situation A. So we suddenly replace the mass. Suddenly replace M1 with M2. All right, so let's just look at what we have here. So again, we use conservation of energy as well as the pressure, meaning this gas exerts a pressure and it has to balance the pressure of the mass above it. So what is our energy equation? Well, we have the gravitational potential energy of the mass. So for situation 1 on this side, we have an you would think it would be an M1G, but it's not, because this is immediately after we replace this M1 with M2, right? Before the gases had time to act on it. All right, so we actually have an M2 G, right, and then a Z1, okay, plus the energy of the gas. So the energy of an ideal gas is 3/2 NKT. So we put 3/2. N stays constant throughout this whole process. We're not letting gas in or out. And we have the Boltzmann constant, and then we're under situation 1, so we start with a T1. All right, and the energy, we still have energy balance and everything. So over here in situation 2, right, the only things that are going to be changing here are, we still have an M2, right, because it's after we've replaced the mass. This time it's at height Z2, so we have an mg Z2 plus 3 halves n kb, and this is a T2. Okay, so this is one of our equations from conservation of energy. Now let's look real quick at the pressure. So the weight of this mass is going to balance the pressure of this gas. So pressure is force per unit area, so we have an m1g, so that's the weight of this mass, divided by the area, whatever the area of this piston is, okay? So that's the force going down, and that is, or this is the pressure, right? And this is equal to n kb T1 divided by the volume. I'll just write that. And then we're going to express the volume in terms of Z1 multiplied by the area of the piston head, right? Okay, so let's see what this can tell us. We just have an M1G, all right, so we're just going to get rid of this A real quick. And why not? Let's bring up the Z1. All right, and we can do the exact same process for this situation number 2. We didn't make any specific statements about any of this, so basically we get exactly the same equation here, but with just the ones just replaced by 2's. Everything we said was general, so we can just write out our second equation here. Okay, so let's see what we can do with this. Now what we want to do is use this along with our energy equation, along with this, and let's see what we can do here. Well, we can, our original goal was to find these 2 ratios. So one thing we could do is go ahead and divide these 2 equations, and that will give us, one in terms of the other one. So one thing we can do, I'm just going to go ahead and flip these, right? So rather than express T1 over T2 by just dividing these equations, since we're shooting for 2 over 1, I will just flip it. So we have a T2 over T1 equals, and then flipping this side, M2Z2 over M1Z1. Okay. All right. So now we want to go ahead and maybe we can get this equation only in terms of temperatures, all right? So what we want to do is get rid of Z1 and Z2. Once it's all in terms of temperatures, we can find the ratio of our temperatures. All right, so let's just solve real quick for for Z1. Hey, let's go back and use these equations real quick. So if we have a Z1, it's equal to this n kBt, or T1, divided by M1G, okay? And using this equation is to, again, we can just replace the 1 with a 2. So T2 this time, and an M2G. All right, so let's go ahead and put these up in this equation so we get rid of our z's. And so the first thing we're going to do is solve for this ratio of, what is it, T2 divided by T1. And then we already, once we know that, we have this, once we know that ratio, then we already have this Z2 over Z1 expressed in terms of this. So we should be good to go. All right, here we go. So I'm going to write this M2G. Now we need to plug in our Z1, which we found right here. So we have an N kBt, this is a T1, divided by M1G, okay? Now we can put in this term, 3 halves N kBt1, all right. M2, now I'm onto this term, M2G. Now we need to plug in our Z2, which is right here. And kBt, this is a T2, and this is divided by M2G, right here. Okay, and we have one more term, which is just 3 halves N kBt2. I'll write that right down here. Okay, great. So now we have all T1s and T2s, no Z's hanging around, and we'll go ahead and see what we can do with this. So we can divide out this G. We can divide out M2G here. All right, so when we are going to, what should we do? We need to factor out a T1. So I'm looking at this side here, and this T1 needs to be factored out. We also have an NKB that can be factored out, I guess. You know what, let's just divide by NKB in all 4 terms. Okay, that's easy. All right, we don't have to deal with that now. So we factor out our T1 here and here. We have an M2 over M1 from right here, okay, and a 3 halves left over. So here's our left-hand side. Now moving to the right-hand side, we can factor out a T2. And that was the only guy left up in this one, right? Here's the T2, and all we have left on this side is a 3 halves. So we have a 1 from up here plus a 3 halves. 1 plus 3 halves is a 5 halves. Okay, 5 halves T2. And let's go ahead and I'll start a sort of a results sheet. So this was for our situation A, where we replaced the mass suddenly, right? And here we have T2 over T1, okay? So what we're going to do is we're dividing both sides by T1, right? Take this guy over, and then we'll take this 2/5 and flip it and multiply over here, okay? Let me just double check and make sure. Yeah, we're solving for, right, we're solving for, yeah, we're solving for 2 over 1, T2 over T1. All right. So we've divided T1 over. Now we need to have a 2/5, and this is an M2 over M1, right? So take this and divide it on over here, all right? And then we get a 3/2 multiplied by 2/5. So the 2's cancel out and we get a 3/5. Okay, so here is our first result, the ratio of temperatures. This is for A, which is sudden. I'll just write that here. The sudden replacement of the mass with the other mass. All right, so I'll set this paper aside just so we can come back to it later when we have more results to put on it. And what we have now is we need to go back and use this guy right here to get the ratio of the z's. Let's just start a new page here. Okay, so if I rewrite this z2 over z1, all right, this right here, okay. Now I'm just going to write an m1 over an m2 multiplied by t2 over t1. So all I did was flip this over, okay. All right, so now we are going to, all we have to do is plug in our t2 over t1. So from our sheet right here, we have m1 over m2, 2/5, m2 over m1. I'm going to go ahead and just distribute this through. So I'll write this m1 over m2 again. All right, now we see, hey, these guys will divide out for us, so there we go. And here we are, we're left with our answer for z2 over z1, which is, let's start on this side. So we have a 3/5 m1 over m2 plus a 2/5. Okay, and notice real quick that when m1 is equal to m2, right, so this goes to 1 and this goes to 1, we have a 2/5 plus 3/5 or 3/5 plus 2/5. So those both give us a 1 for this ratio as well, meaning the temperature stays the same, the height stays the same, and everything behaves the same, just like we would expect. All right, so now we'll look at situation B, which is a very gradual transition from mass 1 to mass 2. And so in this case, again, we have diathermic walls, no heat transfer through the walls. And in this case, because it's very gradual, it is quasi-static, and we can call this an adiabatic process. So this one's fairly quick. What we've got for an adiabatic process, when we have a T multiplied by V to this gamma minus 1 is constant. And this gamma is the ratio of the heat capacities at constant pressure and constant volume. Okay, so for this ideal gas, gamma is equal to 5/3. So what this tells us is that we have T1 multiplied by, so the volume, which is A, which is just the area of the piston, right, multiplied by Z1, so there's the volume. And then gamma minus 1 is, what is that? That leaves us with 2/3. Okay, there's 2/3 left. All right, and since this is constant, it will be equal to the same thing after our process is complete. Since we haven't changed the number of gas particles or anything like that. So this time we have a T2, a Z2 to the 2/3. Okay, so obviously this A is going to divide out. And let's go ahead and we'll start with the T2 over T1 case. So this is equal to, we have a Z1 divided by a Z2. And this is to the 2/3 power. All right, now one thing that still holds in all of this is, well, I guess conservation of energy would, well, so we still have this, this pressure balance, right? We still, at the end points, we still have the weight of the mass balanced by the pressure of the gas. So these equations that we came up with earlier still hold. So what we're going to do again is take out these z's and put in t's using these equations. All right, so obviously this n kV over g, that part is going to be the same on both of these, and that part will cancel out. So for Z1, we have a T1 on top and an M1 on the bottom. For Z2, here on the bottom, we'll have the T2 on the bottom and an M2 on the top. And this is to the 2/3 power. All right, so now we want to just bring these t's over here, right? So basically we'll end up with a T2 over T1. And when we bring a 2/3 power and flip this over here, we get a 5/3. This ratio to the 5/3 power is equal to M2 over M1. And this over here is still to the 2/3. All right, so we can take the cube of this immediately, and we just have a fifth and a square over here. We'll take the 5th root of this to get our final ratio here. So we just have an M2 over M1, and this is to the 2/5. All right, so we have this added to our, for the gradual case of B, we have T2 or T1 equals M2 over M1 to the 2/5 power. Okay, so now we just have to do the same thing, except this time we're going for the Z2 over Z1. So if we look at this equation right here, all right, we have a Z2 over Z1 is equal to, we'll take the 3/2 power of both sides, and we're flipping it as well. T1 over T2, and this is the 3/2 power. Okay, and all right, we already have this ratio basically, right? So this this is flipped upside down, so we have an M1 over M2. And it's to the 2/5, and then it's to the 3/2. Okay, so these 2's will divide out. We have a 3/5. So we'll put that over here. We have Z2 over Z1 equals M1 over M2 to the 3/5. And there we go. These are the quantities we were asked to find for this for this gas in this piston with a mass on top. You can see, of course, when the M1 is equal to M2, these go to 1, just like in the case up above. But yeah, you can see the difference in the situation when we have a sudden replacement of M1 with M2 versus a very gradual, where we very gradually take mass off. And these ought to be general, whether or not M1 or M2 is greater. So we went with a case where M2 is less than M1, but should be just equally applicable to a case where M2 is greater than M1.